Hello everyone, welcome back to our series on chapter 17. Today we are working again still with titrations. This is part 5, putting it all together, and I'm going to say that this is putting it all together part 1 because there's a second piece to making sure that we understand what a full titration looks like. So let's get started. So when we collect data while doing a titration, we have been measuring the pH versus the volume of titrant added. And so in this case, we have a strong acid in our burette, HCl, and we have a weak base. This is our acetate, our weak base in our flask. And so the pH, this is of the weak base solution. The volume of HCl added, this is from our burette. And so what we do is we collect the data points along the way. And it doesn't matter how often we collect data points, really. What matters is that we get data points across this entire curve. Now, we like to label these different regions of the curve based upon what is in solution at that point. And so, for our example, at the beginning, this is when no HCl has been added. What we have is a weak base, our acetate ion. And then once we start adding HCl, we enter into what is known as the buffer region. And so in this region, the pH is controlled by both the weak base, the acetate, and the acetic acid within the buffer region. At some point, we break our buffer, and this is what I like to think of as the equivalence. Hold on. I can't spell equivalence. Equivalence. There we go. Equivalence region. And the midpoint of this region is the equivalence point. And then beyond our equivalence region, this is when we have strong acid in solution. And so at this point, we have excess HCl. And so the HCl is controlling the pH. And remember, at the equivalence point, this is when all of our weak base has been turned into conjugate acid. So at the equivalence point, the pH is controlled by the weak acid. Okay, so the previous videos walked through how to do the calculations for each of these important points along the titration curve. It just turns out that as the titration is happening, all of these points end up occurring. And so it's really important to know where you are, what is in solution, in order to figure out how to find the pH at that point along the titration. So another way of explaining this is dividing this up into 3 regions. And so we have region A. This is our buffer region. We have region B. This is our equivalence region. And we have region C. This is our strong region. And ultimately, with a titration, what we want to find is the equivalence point. And in order to find the equivalence point, we have to find the midpoint within this equivalence region. And so to do that, what we try to do is we try to find the intersection of the buffer region with the equivalence region and the strong region with the equivalence region. So these are the intersections of the regions. And if we know our intersections, we can find the halfway point between those, or the midpoint between those. And so this is some example data. What I've done is I've graphed this with 3 series on the same graph. Now, you do not have to have these all on the same graph, but what I've done is I've looked for region A. I found the equation of the line of best fit. I did the same thing for region B and the same thing for region C. I'm going to use these equations of the lines in order to find the intersection points of this data to be able to analyze this hypothetical titration. Back, now I know these 2 points. And for me to find my midpoint between those, or my equivalence point, I need to find the halfway point between these 2 points of intersection. So the first step along this is to find the intersection of region A and region B. So remember, region A is the point of the buffer region, so the points before the equivalence point, and region A had the line of best fit of y equals negative 0.2386x plus 13.14. And region B had the equation of best fit of negative 2.6x plus 42.6 y equals. So in order to find the point of intersection, the point of intersection is where the x and the y values for these 2 lines will be equal to each other. And so what I can do is I can set these 2 equations equal to each other. So I have negative 2.386x plus 13.14 equals negative 2.6x plus 42.6. And if I do my algebra, I can rearrange this and I get that 2.3614x is equal to 29.46, and I find that x is equal to 12.48. And now the x values is milliliters. So to get y, what I am going to do is I'm going to plug this value for x into my region B equation. Now, there's not really a reason that I chose region B. You can choose region A just as easily, and you'll get an answer that is just as valid. So I'm plugging this in, so I've got negative 2.6 times 12.48 plus 42.6. And if I solve this, I get that y equals 10.152. And so this point of intersection is equal to my x is 12.48, comma my y value 10.152. And this is an answer that we're going to use. Okay, flip. So now in the next step, we have to do the same thing again, but we need to do the intersection between region B and region C. So for region B, my line of best fit is negative 2.6x plus 42.6 is equal to y. And region C, my equation is negative 0.1x plus 5.45 is equal to y. And so I'm going to set these two equations equal to each other. So I get negative 2.6x plus 42.6 equals negative 0.1x plus 5.45. And if I do the algebra, I get that x is equal to 14.86 milliliters. And I'm going to plug that value in. And so y is equal to negative 2.6 times 14.86 milliliters plus 42.6. Y, it becomes equal to 3.964. And so my point of intersection is going to be my x value, 14.86, comma my y value, 3.964. Okay, so now I know. Now I need to find the midpoint of region B. And so I have my point of intersection between regions A and B. My first one is 12.48, comma 10.152. And point 2, my lower point of intersection between region B and C, is 14.86, comma 3.964. And so what I have to do is I have to find the midpoint between these. Now, the midpoint formula is that the point is x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So it's basically the average of the x values and the average of the y values gives us a data point. And so my midpoint is equal to 12.48 plus 14.86 divided by 2, comma, 10.152 plus 3.964 divided by 2, which gives me the data point 13.67, comma, 7.058. And I know things from my graph that when I graphed this titration curve, looks something like this, I had volume of HCl on my x-axis and I had pH on my y-axis. And so that means that this y point corresponds to pH and this x point corresponds to volume of HCl. So, what can we do with this information? This volume of HCl required to reach the equivalence point is very key. Because from volume and concentration, we can find moles. And so using the volume of HCl, we can use this to find the concentration of the acetate in our example. We can also use this to find the pKa of the acetate. And this is what you are expected to do in the first laboratory assignment. Okay, so in the next step, in the next video, I'm going to talk a lot more about how we use this volume of the HCl to be able to find our concentration of our acetate and our pKa of our acetate ion. Okay, so stay tuned. Remember, keep checking World Class, send me emails, post on the discussion board, come to office hours. I'm here to help you and support you through this transition. Have a good day, and I will see you later.